Hello, everyone. Today we're going to talk about Lesson 8, Single Replacement Reactions. But first, I want to take a minute to go over the answers to the decomposition reactions from our previous lesson. So, if we look at example number 4, we have magnesium chloride breaking down into magnesium and chlorine. Now, this is a decomposition reaction where we have a compound breaking down into the individual elements that make up that compound. Remember that when we have chlorine, we have a diatomic, so it has to be written with this 2 down below here. In our second example, question number 5, we had potassium carbonate. Carbonates, remember, break down into carbon dioxide, and then what's left over is our metal oxide, in this case, K2O. So in writing this, potassium is a +1, oxygen or oxide is a -2 charge, which is why we need 2 copies of potassium when we write our final formula. And finally, we have magnesium chlorate. Remember that chlorates break down into metal chlorides, and oxygen. Oxygen, again, is another diatomic, which is why we need the 2 down there. And in this case, our metal chloride is magnesium chloride. So magnesium is a 2+ charge, chloride is a 1- charge. So we need 2 copies of the chloride in order to balance that out. We're going to go on and take a look at question numbers 7, 8, and 9. In this case, we have an acid, but because it's just a binary acid, the only outcome for this is to break down into its 2 components. So we have hydrogen and iodine. Remember, hydrogen and iodine are both diatomics, which is why we need to put the 2's in here. In our next example, we have a metal hydroxide. With a metal hydroxide, we're going to break that down into a metal oxide, barium oxide in this case, and water. So barium, just as a reminder, is in group 2, so it's 2 positive. Oxygen is in group 16, so it's 2 negative. So our 2+ and 2- cancel out here. Water, of course. Number 9 is a little bit different, and it doesn't really fit any of our other examples. However, this is something that we're going to learn about. So in this case, we have ammonium hydroxide. Ammonium hydroxide, when it decomposes, breaks down into ammonia and water. So if I were to draw a picture of what this looks like, we have NH4OH. So you can kind of see how the water is right here, and then the remaining part, the ammonia, is what is left behind after that water separates from it. Looking at our final 3 homework problems, we have this time a polyatomic acid. So a polyatomic acid, remember, is made up of water and a non-metallic oxide. So water, in this case, our non-metallic oxide is carbon dioxide. In question number 14, we have another example of a metal hydroxide, similar to the barium hydroxide that we had earlier. And very similar, we get magnesium oxide, remembering that magnesium is 2+, oxygen or oxide is 2-. Finally, we have barium chlorate. Here's barium chlorate here. Chlorates, remember, decompose to give you metal chlorides. So barium is a 2+, chloride is a 1-, which is why we need a 2 here next to the chloride, and then, of course, oxygen. So you can see behind me the general format for a single replacement reaction. In this case, we're always going to start with at least 1 compound and 1 element. And what you're going to notice here is that the element is going to replace part of the compound. Now, it could replace the A or the B, depending on whether that element forms a positive charge or a negative charge. So in the example that I made, I chose an element that forms a negative charge. So maybe something like chlorine replacing iodine or iodide in a compound. So in this case, the element is going to replace one of these. The X will end up by itself down here. And now the Y, which was originally the element that was by itself, is now part of the compound. So we have a compound reacting with an element, forming a new compound and a different element. So right now we're going to take a look at a single replacement reaction demonstration. Okay, in the demonstration you just watched, we took a piece of copper metal, which was a solid, and we added it to a solution of silver nitrate. That was our colorless liquid that we used there. And what happened was the silver from silver nitrate was replaced by the copper, forming copper 2 nitrate, CuNO3 2, That was our solution, and silver metal, which was our solid that formed. So copper, we know what copper looks like, similar to a penny. We have this colorless solution. Now you can see after the reaction, we have our blue solution, and then finally our solid product. When this equation is balanced, we're going to have 2 silver nitrates. That accounts for the 2 nitrates here, and then 2 atoms of silver. The rest of these are ones. So I hope you enjoyed that demonstration. Okay, we're now going to take a look at some single replacement reaction examples. There are about 3 different types of these that we're going to talk about. So in the first part, you see an active metal will replace a less active metallic ion in a compound. Now, this is the first time that we're going to see anything like this, the possibility of no reaction actually occurring. So if we are to determine whether or not a metal is more or less active, we need some kind of chart that tells us the activity for each metal. So in this case, anytime you're asked to do a single replacement reaction, I'm going to provide you with what's called an activity series. The activity series will tell us which metal or non-metal, depending on what the single replacement reaction is less active. The less active metal, the one that is lower down on the chart, should be the element that is by itself at the end of the reaction. So let's take a look at our first example. We have aluminum metal, and it's reacting with lead-2 nitrate. So aluminum and lead. Because aluminum forms a positive charge, it's going to replace the thing that also forms a positive charge. So in this case, that will be the lead. So if we compare aluminum and lead on our activity series, here is our aluminum, here is our lead. Notice that the least active elements are at the bottom of this, the most active are at the top. We want the least active metal to be by itself at the end. Right now, the least active element is part of a compound. So on the right side of the equation, we're going to write lead by itself as a solid. And then we're going to write the formula for the new compound that forms between aluminum. Aluminum is 3+, and nitrate. Nitrate is NO3 1-. So the new formula is going to be AlNO3 3. This will be aqueous. Balancing this equation. Since we have 2 nitrates on one side and 3 nitrates on the other, we're going to find the least common multiple, which is 6. So I'm going to put a 2 in front of the aluminum nitrate, 3 in front of the lead-2 nitrate, and that will cause me to form 3 lead atoms, and of course I'll need 2 aluminum atoms in order to do this. Let's take a look at our second example. A less active metal will not replace a more active metallic ion in a compound. So in this case, we're comparing silver and magnesium. So again, we want the lower element to be by itself at the end of a reaction. If it turns out that the lower element on the activity series is by itself at the beginning of the reaction, then no reaction will take place. So we have silver. Silver forms a positive ion, so it's going to replace potentially the magnesium. So now we're going to compare. Here's silver, here's magnesium. Silver is much lower and less active than magnesium. It is already the element that is by itself. So when you have a case like this, we have a no reaction here. One of the benefits of making jewelry out of silver, gold, or platinum is that they are not very reactive, and that makes them more valuable. Notice that those precious metals are all down here at the bottom: platinum, gold, and silver. We would not want to make a ring or a piece of jewelry out of something like magnesium, which is going to react with moisture in the air and oxygen. So instead, we choose to make metals or jewelry out of metals that are non-reactive. Our third and final type of single replacement reaction deals with group 1 and 2 metals reacting with water. So when either a group 1 or 2 metal is added to water, it produces a metallic hydroxide and hydrogen gas. So in this case, sodium is going to replace the hydrogen in water forming. Now, it may help if you consider water as an H plus and an OH minus that are stuck together. That makes this look just like any of the other single replacement reactions. Sodium, which forms a positive charge, is going to replace the positive charged part of water. Thus, we'll form sodium hydroxide plus hydrogen gas. Balancing this equation, we're going to get 2 sodiums, 2 waters, so we have 4 hydrogens, 2 hydrogens here plus 2 more. So we have 4. 2 oxygens, 2 oxygens. This same reaction could take place for an element that is in group 2. So for example, if we were to see magnesium react with water, same thing here. We would still want to break this up so it looks like H plus and OH minus, even though it doesn't officially break up, but it helps us to figure out what our products are going to be. So we would have magnesium hydroxide. Magnesium is 2 plus, hydroxide is 1 minus, which is why we need 2 copies of them. And then finally, hydrogen gas. So by doing this, we would need 2 waters here. That'll give me 4 hydrogens, 2 plus 2 more, 2 oxygens, 1 magnesium, 1 magnesium. So in this case, we would have coefficients of 1, 2, 1, and 1. Now, let's take a look at a few homework problems together. So just like last time, our homework problems are going to consist of 2 parts. First, I would like you, those of you in accelerated honors, to complete the chemical formula equation based on one of the 3 reaction types we just saw for single replacement reactions. Then, once you have completed and balanced your equation, write out the equation in word format. Let's take a look at our first example. We have zinc reacting with lead 2 nitrate. Now, as a reminder, we need to go back and check our activity series for these 2 elements, zinc and lead. If you look at our activity series, we can find zinc and we can find lead. This one should be by itself at the end. Currently, we have lead as part of this compound. So in this case, we will get a reaction so that lead ends up by itself at the end of the reaction. So we have Pb plus, and we can leave off states of matter for now, zinc nitrate. Now, zinc nitrate is going to be ZnNO3 2. Remembering, of course, that zinc is a 2 plus charge, nitrate is a 1 minus charge. That 2 plus charge for zinc can be found on your common ion sheet. Okay, balancing this equation. We have 1 zinc, 1 lead, 2 nitrates, 2 nitrates. So all of our coefficients end up being 1. And now we can write out our equation. So we have zinc plus lead 2 nitrate. You can also write plumbous nitrate forms lead plus zinc nitrate. Zinc is not a diatomic, so it's not going to have any Roman numerals. And then, of course, all of our coefficients end up being 1s. Okay, taking a look at our second example, we have potassium reacting with barium acetate. Now, if you remember from looking at the chart, potassium is one of our most reactive metals. So barium is definitely lower on the chart than potassium. Now, in this problem, what we're going to do is say that potassium is going to replace the barium, the positively charged part of barium acetate here. So the new compound that forms is going to be potassium acetate, which is going to be KC2H3O2. Some of you might be wondering, how come I didn't have to use parentheses? Well, remember that K is +1, and acetate is a polyatomic ion from your common ion sheet with a -1 charge. So the +1 and -1 cancel each other out. We need just one copy of each. The other part of this is going to be barium. Barium is going to end up by itself over here. Balancing this out, we're going to have one barium, two copies of acetate. So I need to put a 2 in front of that, which means I need 2 copies of potassium. These will both end up being 1s. Writing out our final equation, we have 2 potassium plus 1 barium acetate forming 2 potassium acetate plus 1 barium. Okay, there are 3 different parts to this homework assignment, so I wanted to show you a few examples from each part of the homework assignment. In part 2, we run into the possibility of having a reaction or not having a reaction. So let's take a look at these 2. So in this first problem, we have potassium reacting with copper 2 chloride. So again, we're going to look on our chart. We're going to find where potassium is. That's way up here at the top. And we're going to find our copper. Copper is way down here at the bottom, just above silver. So copper should be by itself at the end of this reaction. So we will have a reaction here that isolates copper and then is going to produce for us potassium chloride. Remembering, of course, potassium is +1, chloride is -1. When I balance this equation, we have 1 potassium, 1 potassium, 1 copper, but I have 2 chlorides here. So I need to put a 2 in front of the potassium chloride and then a 2 in front of the potassium. So our final equation in this case is going to be 2 potassium plus 1, and this could either be copper 2 chloride or cupric chloride. We'll just switch it up here just to keep it fresh in both formats. We have 1 copper plus 2 potassium chloride. In our second example, what you need to look at is the second part of the activity series. So if you note, on the second part of the activity series, we have just 4 elements. So there are more, but we're only going to focus on these 4 elements that can replace each other. The reason why they're separated from that top group that you see over here is that these 4 elements are the only 4 that we're going to be responsible for that form negative charges. So if you look at that list, it's just in the same exact order that we see in group 17. So we have F2, Cl2, Br2, and I2. So comparing the 2 possibilities here, chlorine forms a negative charge. So it's going to replace the part of the compound that is negatively charged. So now we have to compare these 2, chlorine to iodine. Which one is lower? So here's chlorine on our chart. Here's iodine. Iodine is lower, so we want iodine to be by itself at the end of this reaction. So we're going to have I2 plus HCl. Remember, of course, iodine is a diatomic, which is why it needs the 2. And then your compound of KCl is formed from a K plus, group 1, and a Cl minus in group 17. Balancing this equation out, we have 2 chlorines, so we need to put a 2 in front of the potassium chloride. Now we have 2 potassium, so we need to put a 2 in front of the potassium iodide, and that will also give us the 2 I's that we need. These both end up being 1s. Now we can write out our equation. So we have 1 chlorine plus 2 potassium iodide yields or produces 1 iodine plus 2 potassium chloride. And we'll look at these final 2 examples, number 9 and 10. So in this case, you're presented with an equation in word format, and you have to kind of switch that into formula format. So it says a piece of steel wool, which is iron. So we're going to start off with iron here, is placed into sulfuric acid. So we have H2SO4 over here. Now we're going to compare. Iron forms a positive charge. So it's going to replace potentially the hydrogen part of sulfuric acid. So let's compare those two. Here's iron. Here's the hydrogen. Notice that it's the only nonmetal in this group. Hydrogen is lower down on the table. So hydrogen is actually going to form as a result of this reaction. So we're going to get hydrogen by itself, and our other product is going to be iron 2 sulfate, so FeSO4. Fe is 2 plus, SO4 is 2 minus. My recommendation to you is this. If you are not made aware in the problem of what oxidation state, what charge a divalent should get, use the +2 oxidation state as the default. So if the problem tells you to use iron 3 plus, then by all means do that. But if you're not given any notice, use the 2 plus as the default. So in this case, balancing this equation, I have 1 iron, 2 hydrogen, 2 hydrogen, 1 sulfate, 1 sulfate. So all of these can end up being 1s. You don't have to write out a word equation for these last few problems. Let's take a look at our last example. We have a piece of silver jewelry. Means we have silver is dropped into hydrochloric acid. So silver, a metal, it's going to form a positive ion. We have to compare silver to the positive part, which is the H, for HCl. So we're going to look at silver, that's down here. We're going to look at H again, that's over here. Notice the silver is lower. So this is our second time where we encounter something that is a no reaction. So in this case, silver wants to be by itself. It is already by itself. So we can just write no reaction as the answer to this equation. Okay, if you have any questions, please consider stopping by office hours on Thursday for extra help. Thanks, everyone. Have a great week.